feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional lesson with Mr. Gaines here as we continue our discussion on systems of equations. So up to this point, we have looked at linear systems of equations in both 2 variables and 3 variables. Now we're going to progress a little bit further and take a look at systems of equations that could potentially be things other than lines. So when we talked about solutions for linear equations, really what we did, if you think about this graphically, what we were doing was we were taking a look at intersection points for lines. So if a solution had a single system, it looked something like this, where we had one point where the systems intersected. If the solution had all solutions, it would look something like this, where the 2 lines were overlapping and so they shared all points. And if we were looking at systems that had no solution, it would look something like this, where the 2 lines were parallel, thus not having intersections. So when we looked at linear systems of equations, their solutions graphically were intersections of the lines. The same thing can be true about nonlinear systems of equations. So nonlinear systems combine potentially a line and another type of function, some that we have learned in Algebra 2 this year, some that you've learned previously in Algebra 1 or geometry. Or it could be looking at systems including a variety of different functions, some of them not even having lines. So if I take a look at the examples that I have on the screen, when we take a look at possible solutions for a nonlinear system, basically if I graph them, I'm looking for intersections. So in both of these cases, here on the left I have a parabola and I have a line, and on the right I have a circle and I have a line. And based on what we know about parabolas and circles and lines, we know that these are not going to intersect. So this would have no solution. So these 2 systems of equations would be what we consider inconsistent. There is no solution. If I take a look at the same type of graphs, now a line and a circle and a line and a parabola, you'll notice that they intersect in exactly one point. They're tangent lines, and you probably learned a little bit about tangent lines in geometry. We're not going to go too far into what a tangent line is or its concepts, but what we're looking at is that this line intersects in exactly one spot. So the solution for this parabola and line would be the point 2, 3. The solution for this circle and the line would be the point 1, 2, and so these would have one solution. Now we can expand on that. With lines, you either had no solution, one solution, or all numbers would end up being solutions. With nonlinear systems, we're going to find that there's more scenarios. So again, we're looking for solutions to be intersections of the graph. So if I look at this line and parabola on the left, they intersect in 2 places. If I look at this line and this circle on the right, they intersect in 2 places. These 2 graphs, or these 2 systems of equations, would have 2 solutions. And so that's not something you saw with linear systems of equations. We can now, if we go nonlinear, have 2. We could have more. So notice here that I have a parabola and a circle on the left. This has 3 solutions. So we see 3 intersections. Now they do share a common point. Notice an intersection doesn't have to be passing through. So this parabola's vertex is on the circle, and so it doesn't really pass through that point, but it is an intersection, so we'd have 3 solutions. To the right, I still have a circle in the same location. I've shifted my parabola down, and this one gives me 4 intersections and thus 4 solutions. And really what we're going to find is once we start looking at certain types of polynomials combined with potentially circles or other functions, there's actually an infinite number of solutions. So here's an example of a graph that I created that is a polynomial, a function. You may notice this as a cubic function, and a circle. And here we see 1, 2, 3, 4, 5, 6 solutions to this function. So depending on how many curves the polynomial has and the size of the circle, we could pass through more than this. We could pass through actually an infinite number of times. So solutions are not going to be set to just one or nothing else in terms of nonlinear systems. It's going to be potentially looking at multiple solutions. So in problem number 1, here's an example where we have two systems of equations, and it says determine the number of solutions for the below system. So what we're going to do is we're going to use the graphing calculator to help us graph. Now, some of you may be able to sketch out a coordinate plane and graph x squared plus y squared equal to 25. It'd be a circle centered at 0, 0 with a radius of 5. And then we could probably rewrite the equation for x minus y equals 1 into y equals x minus 1, which would be a linear equation, and we could take a look and graph both those and see the number of intersections. In this case, it's probably not too difficult, but in most cases, or in some cases, we're going to want to use the graphing technology. We're not going to want to graph extreme polynomials by hand. We've done that already, so we can, but the graphing calculator is going to save us some time. So what I'm going to do instead here is, instead of graphing this by hand, is just graph it using the calculator. Now again, as we've seen previously, the calculator requires that y is isolated. So I'm going to start with equation b. This is going to be easier to rewrite. So I'm going to rewrite b by subtracting x from both sides. So this would be negative y equals negative x plus 1. And then I would divide by negative 1, so y equals x minus 1. So that's how I'm going to rewrite b. And then I'm going to rewrite a. A is going to be a little bit more in depth. I would want to get, again, y by itself. That's what my calculator requires. So I would have y squared equals negative x squared, as I've subtracted x squared from both sides, plus 25. Then I would square root both sides. So remember, when we create the square root in what is essentially the solution process, we need to make sure we have plus or minus. So this would be plus or minus the square root of negative x squared plus 25. Now, you can graph that in your calculator depending on what calculator you have. Some of them do have the plus or minus option, some of them do not. So I'm going to show you what it would look like if you do not have the plus or minus option. We would graph x minus 1, y equals x minus 1. Then I'd graph the square root of negative x squared plus 25, making sure the negative x squared plus 25 is inside my root or inside parentheses. And then the opposite of the square root of negative x squared plus 25. So I'm really taking care of this plus or minus root here with two different lines. Now I can graph this on my standard window, and I can see my line is drawn through here, and I can see my circle is drawn here through here. Now this is a rectangular grid. If I want this to look more circular, I can hit zoom and go down to 5, which will turn it into a square grid. And there you get a better picture. It looks more like a circle. But I can see here that there are two intersections. Now again, depending on your calculator, some calculators will close this circle where you'll see it drawn all the way through. Some will not. So make sure that you realize that there's not supposed to be a gap, that this is a complete circle based on the calculator's operation mechanism. Sometimes it does not show that. So back to the question. The question was to determine the number of solutions. If I take a look at that graph, I can see two intersections, and thus we have two solutions. Now, let's work at finding the solutions. I could find the solutions of these algebraic or graphically if I wanted to go to second, trace, intersect. Then I could find the intersection point, which would give me the solutions. We didn't have to do that in this problem, but that is an option that we have. So in problem number 2, it actually says use an algebraic method to find the solution to each of the following systems of equations, if one exists. So sometimes there is no solution. And check your answer with a graphing utility. So when we're dealing with non-linear systems of equations, it is most commonly easier to solve algebraically through substitution. So we did both substitution and elimination up to this point. In the previous target with 3 variables, we focused primarily on elimination. In this case, we're going to focus primarily on substitution. So if I take a look at 2a, I can see that the first equation already has y isolated. So I'll just title them. I'll title this equation A and equation B. So equation A already has y isolated. So I can go ahead and then substitute y into B. Now, I can do this right away, or I can rewrite B so that y is isolated. I'm actually going to rewrite B so that y is isolated first. I'm going to do this because I want to be able to check it in my graphing calculator. And in order to check it in my graphing calculator, y has to be by itself. So b can be rewritten as negative y equal to negative 2x plus 7. Then dividing by both sides by y, or sorry, negative 1, y equals 2x minus 7. So now I have a rewritten form of b. So again, if I want to solve this algebraically, I can substitute now. I can take a and put it into b, replacing the y essentially with x squared minus 2x minus 3 equal to 2x minus 7. This is the same as setting the two equations equal to one another. Now I may notice that this is a quadratic equation. So x squared minus 2x minus 3 equals 2x minus 7 is quadratic. So I want it to equal 0 if I'm going to solve algebraically. So I'd subtract 2x from both sides. I would add 7 to both sides. And this is an easy factorization. This should be x minus 2 quantity squared equals 0. You could also write this out as x minus 2 and x minus 2. Either or would be okay. If I check this, negative 2x, those add together to give me negative 4x. Negative 2 times negative 2 is positive 4, and x times x is x squared. So this would be the correct format. So we can write it either as the binomial, the two binomials, or x minus 2 squared. Here I want to solve for x, so I'd square root both sides, so x minus 2 equals 0. Then add 2, so x equals 2. Now, again, this is only part of my solution, so we're commonly going to list our solution as points. So I have x equals 2, which is good. Now I'm going to take this x equals 2 and substitute it back in to find y. I can substitute it into any equation, a or b, or the rewritten form of a or b. I rewrote b, and that's going to make it easy to solve for y, so I'm going to substitute in there. So y equals 2 times 2 minus 7. 2 times 2 is 4, minus 7 would be negative 3. So my then point, my coordinate pair that I'd be looking for would be 2, negative 3. Now notice that this solution, we only have one solution technically here, but if we're looking at the number of times the multiplicity of this solution would occur twice because we did have an x minus 2 quantity squared equal to 0. It's not something we're going to focus on really in Algebra 2, but the multiplicity of this solution would be 2. So what I can do is then graph A to check this. A was x squared minus 2x minus 3. And I can graph the rewritten form of b, which is 2x minus 7. If I graph the two of those, I can see an intersection. I'm going to put it back in the standard window real quick. You can see what appears to be a single intersection. If you wanted to zoom in there to make sure that that's a single intersection, you could. We expect to have one intersection. So second trace, finding the intersection, would be the fifth option. It'll say first curve. I want to make sure I'm on one of my two equations here, the parabola. And then it'll say second, hit enter. It'll say second curve. I'm on the line now, which is good. I want to make sure I'm on the other. Hit enter. And I don't need to guess, just hit enter. And it's going to give me the point eventually. And sometimes, depending on where you put it, it's going to round it very, very slightly. So this should be an exact 2, negative 3, which is our solution. So we've done this one correct. So we can go through the algebraic process of solving, and we can also use a graphing utility to help us check. Let's go ahead and take a look at another example. Example B. I'm going to, again, title these equations A and B. And I want to, again, solve this algebraically, so I'm going to substitute. In this case, neither y nor x has been isolated in either equation. I'm going to go ahead and rewrite them. So I'm going to rewrite a by adding 1/2 x, and this one should be easy for us. Y equals 1/2 x squared minus 3. I am going to rewrite b. Again, if you just wanted to do this algebraically, wouldn't necessarily need to rewrite b because you can substitute at this point. I'm going to rewrite b to get y by itself, just so that I have the opportunity to graph this. So if I want to get y by itself, I have a subtraction of x squared. So y squared equals negative x squared plus 41. And then I'm going to square root. So y equals plus or minus the square root of negative x squared plus 41. So now I can do some substitution. And again, it does not matter exactly how you substitute this, but I'm going to go ahead and take the rewritten form of a and b and substitute for y, which is essentially the same as setting the equations equal to one another. So 1/2 x squared minus 3 equals plus or minus square root of negative x squared plus 1. Or, sorry, plus 41. Now, if you substitute a little bit differently, the next step is actually going to end up being the same. So what I would do here is I would square both sides. So I'd make sure to square both sides, and so in doing so, I'm going to get 1/4 x squared. So square the first term. Sorry. 1/4 x to the fourth, actually. So square the first term. Then the two terms multiplied together and doubled would be negative 3x squared. And square the second term, or would be positive 9. The other side, when I square root, the square root will be eliminated, so minus x squared plus 41. This is a quartic. Sorry, I wrote down x squared again. This should be x to the fourth. This is a quartic, so similar to a quadratic, we want to make sure it's equal to 0. So I would add x squared to both sides. So this would give me 1/4 minus 2x squared. I would subtract 41 from both sides, so this would give me a negative 32 equal to 0. Now, this one's probably easier to solve if I can get rid of the 1/4. So I'm going to multiply everything by 4. So x to the fourth minus 8x squared minus 128 is equal to 0. Now, this is a quartic. Remember, quartics do factor like quadratics. So I could factor this into x squared and x squared. The second term would have to be one positive and one negative to multiply together to give me a negative 128. Then I would have to take a look at factors of 128. So we can do that in the graphing calculator. If you need that help, we could do a 128 divided by x. And taking a look at these factors, you can see that 1 and 28 and so on and so forth. And we're looking for factors that would have a difference of 8. And we can see 8 and 16. So this would be x squared minus 16 and x squared plus 8. Now I have two factors that multiplied together to give me 0. So I can multiply or set those two factors equal to 0. X squared plus 8 is equal to 0. Now, if I went through the solving process of this, so I'm going to go through the solving process of this. X squared would equal a negative 8, and then I'd square root. So x would equal the square root of, sorry, plus or minus the square root of negative 8. This is going to be an imaginary solution. And yes, we can come up with that imaginary solution. This would be plus or minus 2 root 2 I. But remember, this system is all about finding intersections on a graph. And so this is actually not going to show up as intersections on a graph. So we can kind of, if we realize a factor is going to give us an imaginary solution, we can kind of ignore that. It's going to be a solution that exists for x, but we're really just focused on real solutions right now. That's really going to be our goal. So I would set x squared minus 16 equal to 0. So add 16 to both sides. Square root x would equal plus or minus 4. Now, this is the solution for x. This is not the solution for y. In order to solve for y, I need to take plus and minus 4 and substitute them back into the equation here. And I'm going to go ahead and do that on my graphing calculator, just to save a little bit of time. I'm going to do 1/2 times 4 squared minus 3. And so my first pair, I did a positive 4, would be a positive 5. So my first coordinate pair would be 4, 5. I would do the same substitution with a negative 4. So remember, again, we have x values plus or minus 4. And this would also result in a positive 5. So I would have 2 points, 2 solutions here, 2 real solutions. 4 and 5, and 4, negative 5. Now let's quickly check that in the graphing calculator. So I'm going to type my rewritten form of A that I had as set to y equals. And then I'm going to type in 2 lines here because I'm going to need the positive square root of negative x squared plus 41. And I'm going to need the negative square root of negative x squared plus 41. And when I put those together, I'm going to go ahead and take a look at my graph. I'm going to hit zoom and go down to 5, which is square, so I can actually make it look like a circle. You don't have to, but I'm going to do that here. And I can see 2 intersections. So there are 2 intersections. Let's make sure they are the right intersections. So second trace, intersect. I'm going to move my cursor over close to one of my 2 intersections, hit enter. And then it's going to jump to the circle, hit enter. I'm not going to guess, I'm just going to hit enter again. And so this gives me one intersection, 4, 5. I'm going to do the same process again, second trace intersect. This time I'm going to move my cursor too close to the other intersection. Hit enter. It's on the other curve, hit enter, not going to guess, and it's going to give me negative 4, 5. And so here I have both of the solutions. So here we have taken a look at algebraic methods for finding solutions to nonlinear systems of equations, and then also how we can check those graphically, or in some cases, if we were required to, find those solutions graphically. This looks like a good place to stop. We will continue with our next video looking at more algebraic solutions and then get into some applications. As always, thank you guys for tuning in, and I'll see you soon.